Let's now look at another quantum computational scheme that is based on quantum mechanical phenomenon known as quantum teleportation. Before moving on to quantum computation, let's take a closer look at the quantum teleportation protocol. Quantum teleportation allows us to transmit a state that is in one place to an object to another place. In this case, the transmitted quantum state is assumed to be unknown. Moreover, the nature of physical systems can be different. For example, we can teleport states of light to states of atomic systems. To implement such a transmit, it is necessary to have two additional systems in an entangled state. By the definition, quantum systems A and B are entangled if their common density matrix ρ is not factorized by the direct product of the density matrices of these subsystems. That is to say, the expression presented on the slide does not hold. Here, lambda I is the probability of the system being in the state ρIa, ρIb, and ρIa and ρIb are the density matrices of the subsystems A and B respectively. Quantum entanglement was first seen by Einstein, Podolsky, and Rosen as a paradox that points to the incompleteness of quantum mechanics. In the 1960s, John Bell proposed a way to test the completeness of quantum mechanics. For this, he introduced a basis of strongly correlated states of two systems and proposed an inequality that is now called Bell's inequality. The verification of this inequality shows that there are no hidden variables in quantum mechanics, and the presence of entangled state is one of the important elements of the apparatus. Let's now look at the process of quantum teleportation. For quantum teleportation of the state of one qubit psi, two additional qubits are needed, which are in one of the four Bell states: beta 00, beta 01, beta 10, and beta 11. For definiteness, we will assume that the auxiliary qubits are in the beta 00 state. Alice and Bob each hold one qubit from the entangled pair. In this case, the wave function of all three qubits can be written in the form of a tensor product of two wave functions of two subsystems, that is shown on the slide. Here, the subscript indicates the qubit number. This notation assumes that the first and the second qubits are in Alice's hand and third in Bob's hand. In the next step of the quantum teleportation protocol, Alice brings her qubits into interaction with a device that measures Bell's basis states. The device shows which of the four Bell states is measured. Alice sends this result to Bob via the classical commutational channel. Simply put, she calls Bob on the phone and says that she measured her device. To understand what possible state Bob will have as a result of the described actions, it is necessary to recompose the state of two systems so that the first and the second qubits are on the basis of Bell states. The slide shows such a decomposition. Here, as before, X and Z are Pauli matrices. Given the information about Alice's measurement result and the expression shown on the slide, Bob can choose a transform that completes the teleportation of the unknown quantum state psi. For example, if during the measurement Alice received the Bell state beta 01, then in order to teleport, Bob needs to perform transformation X on his qubit.